Now let's see the definition of the determinants of general square matrices. So let A be a matrix uh, square matrix of n dimension, so n by n matrix. Then we write determinant of A as this, det of A, or like this, A within between bars. Okay, these mean the same thing. Okay, so we define the determinant of the matrix A as follows. We define in a recursive manner. If if n is 1, then the determinant is just A11, because in this case the only element is this A11, right? And if n is greater than 1, then uh, let Aij be the matrix n minus 1 times n minus 1 matrix obtained by removing the ith row and the jth column of the matrix A. Okay, so if we have a matrix like this, we remove the ith row and jth column and concatenate the remaining parts to define a little bit smaller matrix that is called Aij. Okay, then the determinant of A is defined as this, from j equal to 1 to j equal to n negative 1 to the power of I plus j, and Aij. So this Aij, lowercase a, means the ij element of the matrix A times the determinant of the smaller matrix Aij. Okay, so here j runs from 1 to n, and I is any of uh, the numbers from 1 to n. Okay, so this is the definition of the determinant of an n by n matrix. So it's defined recursively. This means when n is, for example, 10, then we need the determinants of 9 by 9 matrices. So there can be many of them, right? And then we need to calculate the 9 by 9 determinants of 9 by 9 matrices. And to calculate those determinants, we need 8 by 8 matrices. And to determine those, we need 7 by 7, and we go down until we reach 1 by 1 matrices. Okay, so in this way, we can calculate the determinants of any matrices of any sizes. Okay, maybe it's easier to see an example. So let's calculate the determinant of this 3 by 3 matrix. 1, 0, 2, negative 1, 1, 1, 0, 1, 0. So these are Aij's. Okay. Then to calculate this, so let us pick the first row as I. Okay. So these are Aij's here. So I is equal to 1. And j runs from 1 to 3. Okay? So the definition goes like this. First, negative 1 to the power of 1, 1. 1 plus 1. Then we multiply by uh, this element, a 1, 1. And we calculate the determinant of a 1, 1 matrix. Okay. And plus negative 1, I is 1, and j is 2, and a1, 2, and a1, 2. Okay, plus negative 1, 1, I is 1, j is 3, a1, 3, and a1, 3. Okay, so what are these matrices? So this is power of 2, a1, 1 here is 1, and this matrix is this part. So we remove the first row and the first column because this is 1 and 1, 1 and 1. So the remaining part is this 1, 1, 1, 0. And similarly, so this is 3, and a 1, 2 is 0. So this term will disappear, but anyway, let us see what this A1, 2 matrix is. So we remove the first row because I is 1, and now j is 2, so we remove the second column. So the remaining elements are this, 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 this. So this smaller matrix is negative 1, 1, 0, 0. And this term, negative 1 to the power of 4, and a1, 3 is 2. And the smaller matrix is now we remove, let's see, we remove the first row and the third column. So the remaining part is negative 1, negative 1, 1, 0, 1. So this part, right? Now, so this is 1, 1, 1 times 1, and we actually we can go back to the matrix of 1 by 1, but we already know the matrix determinant of 2 by 2 matrices. So this is this times this minus this times this. So that is 0 minus 1. And this one is 0 because this is 0. And this one is 1 times 2 times negative 1 times 1 minus 0. So that is negative 1, and this is negative 2, and the result is negative 3. So that is the determinant of this matrix. Perhaps it is instructive to see if the definition of the determinant for 2 by 2 matrices is consistent with the definition of the general determinants. So let's say we have a 2 by 2 matrix, A11, A12, A21, A22. We already defined the determinant of this is to be this times this minus this times this. So it should be this. So this is the first definition of the determinant for a 2 by 2 matrix. But according to our new definition, how does it go? Let's see. So according to our new definition, Let's take the first row as I. Okay, so negative 1, 1 plus 1, and A1, 1. And the remaining, if we remove the first row and the first column, the remaining part is A 2, 2. So this, consider this as a matrix, okay? And then negative 1 to the power of 1 plus 2 times A 1, 2. And if we remove the first row and the second column, then the remaining part is this, A2, 1. So that is, this one is plus 1, and this one is negative 1. So we have A1, 1. And the determinant of 1 by 1 matrix is just that number. So it's 1, A2, 2. And this one, negative 1, times A 1, 2 times A2, 1, which is the same as the previous definition here. So they are consistent. Next, you should calculate the determinant of the general 3 by 3 matrix. Let's say X is Xij is a 3 by 3 matrix. That is X11, X12, X13, X21, X22, X23, X31, X32, X33. So apply the definition of the determinant, then prove that the determinant is actually given by this equation, x11 times x22 times x33 minus x11 times x23 times x32 plus x12, x23, x31 and minus x12 times x21 times x33 plus x13 times x21 times x32 minus x13 x22 x31. So there are in total 1, 2, 3, 4, 5, 6 terms in this expression of the determinant. And you should note that 6 is the factorial of 3. And 3 factorial means the number of permutations of 3 things, 3 numbers, right? And if you look at each of these terms, okay, for example, look at this, then, and also look at the first index, then we have 1, 2, 3, okay? There is no redundancy. 1 appears only once in the first index, and 2 appears only once, and 3 appears only once. And this is the case for all terms. Here, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. Okay? Then look at the second index. Then we have, in this case, 1, 2, 3. Okay, so each number appears only once. And the same is true for all other terms. In the second one, 1, 3, 2, 2, 3, 1, 2, 1, 3, 3, 1, 2, 3, 2, 1. And you can see that the first index always, I have arranged in such a way that the first index always appear appears in the order of 1, 2, 3. And the second index covers all possible permutation of the three numbers 1, 2, 3. So uh, this is the one of the secrets of the determinants. Okay, and also look at the signs. Some are positive, some are negative. So what's the difference? So why some terms have the sign of positive and some has the sign of a negative sign? Okay, now let's consider this. For example, let's take this one. 1, 2, 3. Sorry. 1, 2, 3 is they are paired with 1, 2, 3. Okay, in this case, it's positive. And the next one, okay, so it's 1, 2, 3. They are paired with 1, 3, 2. Okay, in this case, it's negative. Look at this permutation. 1, 2, 3 is permutated to 1, 3, 2. So that is, we have swapped 2 and 3 once. Okay, in this case, we have negative sign. And next one, 1, 2, 3 is paired with, they are paired with 2, 2, 3, 1. In this case, it's positive. Why is that? So, in order to get 2, 3, 1 from 1, 2, 3, we can do, first of all, so 1, 2, starting from 1, 2, 3, let us swap 1 and 2. Okay, then we get 2, 1, 3. So, one step, and then swap this 1 and 3. So leaving 2 alone, we swap 1 and 3 to get 2, 3, 1. So next step. So in 2 steps, after 2 swaps, we get the desired permutation. So in this case, 2 steps is so this 2 corresponds to negative 1 to the power of 2, which is positive, right? So in this case, in the previous case, in this case, it was only one swap. That is negative 1 to the power of 1, which is negative. Okay, same is true for everything else. Let's take the last term here. Okay, in this case, 1, 2, 3 are paired with 3, 2, 1. Okay, in this case, we can swap 1 and 3 once. So that is negative 1 to the power of 1, which is negative 1. So that's the sign here. Okay. So if we can rearrange the order of numbers with even number of swaps, then the sign is positive. If we can rearrange, permutate the orders of these numbers with odd numbers of swaps, then the signs are negative. And you should also note that if one permutation can be achieved with even number of swaps, then it cannot be achieved with odd number of swaps. So this parity, either odd or even, is a invariant property of any specific permutations. Next, we define an important notion called linear function. So, you already know linear functions, but here we give a very general definition. Okay, let V and W be vector spaces. So that means all the these are sets and their elements are vectors. Okay, and both over field K. Okay, but usually we only consider real numbers as the field. Okay, then let f be a function from V to W. Okay, and we say this function is linear if the following holds. One, for all u and v in the vector space V, f u plus v, f of u plus v is equal to f of u plus f of v. And second, for all u in V and for all lambda in K, which is a scalar, okay, lambda is a scalar, then f of lambda u is equal to lambda times f of u. Okay. Remember, this f is a function from V to W. So the result of this function, for example, f of u plus v is a vector in the vector space W. Okay, and so are f of u and f of v. So f of u is a vector within this vector space W. So this lambda times f of u means the scalar multiplication of the vector u of f of u within the vector space W. Okay, so if these two conditions are met, this function is called a linear function. Okay, and this is actually consistent with our notion of linear functions. For example, let's say we have this function. Let's see, f of x is ax plus b, where x is a real number, is a real variable, and a and b are also reals. Okay, so let's say if x and y are real numbers, then x plus y, if we apply the function f, then that is a times x plus y. Oh, wait a minute. So this is not a linear function, so we need to get rid of this. Okay, ax. Then this is ax plus ay, which is f of x plus f of y. So the first condition is met. And let's say lambda is also a real number, then f of lambda x is a lambda x, but that is lambda a x, that is lambda times f of x. So these two conditions are met. So therefore this is a linear function according to our new definition. But the new definition is more general because it's applicable to any vector spaces, any functions, not just one dimension, but any dimensions. Okay, next we show that the determinant is actually a linear function. Okay, so lemma. Suppose A is a n by n matrix, so it's like A11, A12, A1n, and AN1, ANN. Okay, but we represent this as a column vector of row vectors. So that is A1, A2, AN. So each of these is a row vector corresponding to each row of this matrix. Okay. So now the following holds. First, if there is I, that is 1 to n, such that AI is the sum of two vectors. Okay, so so if there is one particular row in this matrix such that AI is a sum of the row vector is the sum of two row vectors. Okay, then we have the determinant of this A1 and at some point BI plus CI and AN. This is equal to the sum of two determinants. Plus A1 CI AN. Okay, so this is the ith row of the matrix, and this is the ith row. So if the ith row is a sum of two row vectors, then this determinant on the left hand side can be split into the sum of two determinants. Okay, and the second, if lambda is a real number, then the determinant of this matrix lambda AI AN, so only one of the rows is multiplied by lambda here. The ith row is multiplied by lambda, is equal to lambda times this determinant AI AN. Okay, so this scalar lambda can be put outside of the determinant. So we have these two equalities. Okay, so let's prove it. I think the second one is quite trivial if you just apply the definition of the determinant. So it's an exercise. So let us prove the first part. So let's see. So this BI plus CI can be written as something like this. BI1 plus CI1 and BI2 plus CI2 and so on, and BIN plus CIN. Okay, so this is a row vector. So if we apply the definition of the determinant, BI plus CI and AN. So if we pick this row, ith row, then the determinant is this: j from 1 to n and negative 1 to the power of I plus j, and b ij plus cij times the smaller determinant. Okay, this aij means the matrix from which the ith row and the ith column are removed. Okay, so that means this matrix does not contain this row. Okay, so but this is just a multiplication and addition of real numbers, so we can just split using the distributive law. So this is just this Bij and Aij plus sum of I plus j, Cij and Aij. But this is the definition of a matrix of this form. So A1, Bi, An. And the same for the second term. A1, Ci, and An. So that's it. So this means the matrix, a determinant, is a function that is linear with respect to each row. Okay, but this applies to any row, right? I can be anything from 1 to n. So this is actually not just simple linear function, but it's called a multilinear function. So multilinear function, because it's linear with respect to many all the rows. The next lemma also shows an important property, yet another important property of the determinant. Okay, lemma. So similarly to the previous lemma, let's consider a matrix as a column vector of row vectors. So we have A1 and so on, and AI and AI prime and AN. Okay, now we swap two rows. So AI is moved to the position of AI prime, and AI, this row vector AI prime is moved to the position of AI. So we construct a matrix like this. A1, everything is the same except for this and this. Okay, so this comes here and this comes here. Okay, we swap two rows. Then their values are related by this. So the sign changes. Okay, if we swap two rows, then the sign of the determinant is altered. Okay, so it's negated. So that's one. And second part, if two rows are the same, so let's see, if we have A1 and so on, and at some point we have A1, and at some point we have another row with exactly the same values as this row. Okay, then the determinant is 0. Okay. Now, once we prove the first part, this part, then proving the second part is very easy. So let's suppose we have already proved the first part, then second part is proved in this way. So if we swap this row with this row, then we should still have the same determinant, right? Because they have exactly the same values. So, but according to the first part, the sign should be negated. So the determinant of, let's say this is determinant of A is equal to negative A if we swap this row and this row. But they still have the same value. But we also have the same value. No, this is swapped version. So these two equations can hold if and only if this determinant is 0. Right? To see this, just calculate this, move this to the left hand side, then we have this equal to 0 and divide by 2, it's 0. Okay, so now let's prove the first part. This is a little bit tricky, and we prove by mathematical induction. Okay, if n is 1, so that is the size of the matrix is 1 by 1, then it's trivial because there's nothing to prove. We cannot swap. And if n is 2, then let's say if we have a matrix like A, B, C, D, then the determinant is A, D minus B, C. And if we swap the first row and the second row, we have C, D, A, B. And then the determinant of this matrix is CB minus AD, right? So CB minus DA, which is minus of this, right? So that's minus AD minus BC, which is minus ABCD. So the claim is true for 2 by 2 matrices. So now, suppose the claim holds for n equal to m. So in the case of m by m dimension, m by m matrices, if we swap 2 rows, then the determinant is negated. So let's assume this. Then now consider m plus 1 times m plus 1 matrix. Okay. And let B be, okay, let's see. The matrix same as A, except that kth and lth rows are swapped. Okay, what we want to show is the determinant of A is equal to negative of the determinant of B. So this is what we want to show. Okay, but let's see how it goes. So the determinant of A, according to the definition, is this. So j from 1 to m plus 1, and negative 1, I plus j, and a, I, j, and a, I, j. Okay, and look, here we said kth row and lth row. And now this I, we can assume this I is different from k or l. Okay, according to the definition of the determinant, we could choose any row for this expression. Okay, so we could choose this I other than KOL. Okay, this is possible if m is greater than 2, right? So therefore, this part, this Aij, this matrix, this is obtained from A by removing the ith row and the jth column of A, right? So this is an m by m matrix. Okay, so that means let's see. That means if we swap uh, the 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 row corresponding to kth row of the original matrix and the lth row of the original matrix, then this should we should have this a ij is equal to negative bij because because of the uh, induction hypothesis. We have this relation for m by m matrix, and these are m by m matrix with two rows swapped. Therefore, this is equal to this one and I plus j and aij uh, and bij times negative 1. Sorry. Times negative 1. But this aij is equal to bij because since this matrix aij and bij are identical except for the two rows other than the ith row. So this aij can be replaced with bij. So that is negative determinant of B. So that is done. Okay, next let me explain an alternative way to look at the determinants. Again, I just use 3 by 3 matrices as an example. So consider this matrix x11, x12, x13, x23, x22, x23, x31, x32, x33, and let's consider each row as a vector. Okay. Then let us define the following unit vectors. So E1 is 1, 0, 0, and E2 is 0, 1, 0, and E3 is 0, 0, 1. Okay. Then we can represent each of these x1, x2, x3 as a linear combination of these three vectors. For example, x1 is x11, x12, x13, right? So that is x11, 0, 0, plus 0x12, 0, plus 0, 0, x13. That is x11 times e1 plus x12 times e2 vector and x13 times e3 vector. Okay, so that means this determinant of x can be expressed as this linear combination of these x11, 1, 2, and 1, 3. So this is the first row, and the second row, 2, 1, and x22, e2, x23, e3, x31, e1, x32, e2, x33, e3. Okay, now we already know that the determinant operation is a multilinear operation. So, for example, uh, let's consider the first row. Okay, then we can split the first row into three determinants, right? So x11, e1, and everything else is the same. Okay, so everything else is the same. And second term, everything else is the same. So this is the same thing. Okay, and x13, e3, and everything is the same. Okay, and we can put each of these coefficients out. So x11 comes here, x112 comes here, and x13 comes here. Okay. Next, we apply the same procedure to the second row. Then this term becomes like okay. This determinant becomes like the first row is e1, the second row is x oh, x x21 e1, and the third row remains the same. Okay, plus e1 x22 e2, and the third row is the same, and e1 x23 e3, and the third row is the same. Okay, and we can do the same thing for the second term and the third term. Then we again split the third row into three terms for each of the terms. So in the end, what we get is this. So that is, in the end, what we get is this: x11, x22, x33, e1, e2, e3. Okay, remember these are all row vectors. And plus x11, x23, x23, and e1, e3, and e2. And now you know what. We will have all possible permutation of three numbers. X1, 2, 2, 3, and 3, 1, and E2, E3, E1, and X1, 2, X2, 1, X3, 3. That's E2, E1, E3. And let's see, what else? X1, 3, X2, 1, X3, 2, and E3, E1, E2. And the last term is x1 3, x2 2, x3 1, and e3, e2, e1. Okay. Now we've seen something similar before, but the difference is here all all terms have positive sign for now, and we still have some determinants to be calculated for each term, right? Now, let's look at this one first, the first term. So this is 1, 1, 2, 2, 3, 3. So this is a permutation that doesn't change. So it has the positive sign. And what's this matrix? This is a matrix of this form. So 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay, so this matrix, right? So E1 is 1, 0, 0, E2 is 0, 1, 0, and E3 is 0, 0, 1. And if you calculate the determinant, so this is, okay, for example, pick this one. So the only non-zero term is the first one. So that is this, and we can ignore the rest. So we calculate the determinant of this, which is 1. So this is 1. Okay, so this has the positive sign. And consider the next term. Oh, next term. Here we have 1, 1, 1, 2, 3, 1, 1, 2, 3. Wait a minute. This should be 2, 3, 3, 2. 2, 3, and 3, 2. Yeah, this should be 3, 2. Yeah. And so this is the permutation from 1 to 3 to 1, 3, 2. Okay. So this 3, 2 comes here. 1, 3, 2. Okay. It's the permutation here. Then this permutation, this matrix is this. That's 1, 3, 2. So 1, 0, 0, 0, 0, 1, and 1, 0, 0, 1, 0. So if we swap the second row and the third row, we get negative sign and 1, 0, 0, 0, 1, 0, and 0, 0, 1. And the determinant of this is 1. So this is negative 1. So this gives us the negative sign. So the same goes on for other terms, and we get the same result as before. So for even for the permutations of even parities, we have positive sign, and the permutations for odd parities, we have negative signs. Okay. Now we have only demonstrated with 3 by 3 matrices, but the same result actually holds for matrices of any size. Okay, so even if we have n by n or like 100 by 100 matrices, we can still apply the same argument. So in that case, these E matrices will have n components. Like E1 is 1, 0, 0, 0, 0, 0, 0, 0 up to like 100. And E2 has 1 only at the second place, and everything else is 0, and so on. And we can still apply the argument of those permutations. And if we swap the rows, we have negative sign. And if we swap 2 times, then the negative sign is again negated to become positive sign, and so on. Okay, here's another important theorem about determinants. Okay, so let's say x and y are n by n matrices. Then determinant of xy. So determinant of the product between x and y is actually equal to the product of their determinants. Okay, so let's prove this, for any n. Okay, so let's say x has these elements xij's, and let's write y as a column vector of row vectors. Okay, so each row of the matrix Y is represented as a row vector. Okay, then and also we again use these E1, E2, and so on up to En. So actually these are the row vectors of the identity matrix, right? So identity matrix, if you remember, this is a matrix with one diagonal, and every off diagonal element is 0. Okay, so this first row is E1, second row is E2, and so on. Okay, then let's calculate the element of xy. So according to the definition of the product between two matrices, this is given as k from 1 to n and xik times yk j. But this ykj is the jth element of the vector yk, right? So this is the jth element of the row vector yk. So let's write that like that. K1, xik, and yk vector jth element. Okay, so this means if we want to calculate the determinant of xy, then this can be expressed as the linear combination of y's, right? So that is x11 times y1. y1 is a vector. x12 and y2 is a vector, and so on. And x1n, yn is a vector. And similar for the second row, x21 times y1, x22 times y2, and x2n times yn, and so on. So the last row is xn1, y1, and xn2, y2, and xnn, yn. Okay, so if you apply the same argument as we did before for calculating the determinants, based on the multilinear property of determinants, we can move every those coefficients out of the determinants. And what we have is something like this. So some summation, let's say it's sum over all permutations of the numbers, n numbers from 1 to n. We have those factors like x1 with some permutation of 1, and x2 some permutation of 2, and xn some permutation of n, with this matrix y permutation of 1, y permutation of 2, and y permutation of n. Okay, So this may look a little bit abstract, but this really means that is this. So we have n numbers from 1 to n. Okay, then we permutate. Is this the right verb? Permutate? Permute? Permute maybe. So this 1 is replaced with some number called sigma 1. 2 is replaced with some number called sigma 2. And n is replaced with some number called n1. So those sigma 1, sigma 2, sigma n, they are integers between 1 and n, including both. So this is permutation. Okay, so these numbers appear as the second index here, and also the index in this determinant. Okay, remove this. And now, if we swap the rows of this determinant, then each time we swap, we change the sign from positive to negative, negative to positive, and so on. And after all, we may obtain this determinant y1, y2, and yn in this order. Okay, but the sign is changed, and let's call that sign as sign of sigma, this permutation. And everything else is the same. So x1 sigma 1, x2 sigma 2, and xn sigma n. Okay, if we swap these rows finitely many times, eventually we are able to get this order 1, 2, 3, and so on up to n, but with possibly a change of signs. Okay, so far so good. Then now look at this part. This part. Okay, this determinant does not include sigma anymore. So this summation means over all possible permutations. Okay, over all possible permutations. For each permutation, we have a different sign, right? And different indices. So now consider this part involving the permutations. Now, let's see. So this is, first of all, the identity matrix can be expressed as this E1, E2, and En. And its determinant is 1, as we have seen before. Okay, so this summation, okay, this summation, if we multiply this summation by the determinant of the identity matrix, that doesn't change. Okay, so sine of sigma and x1 sigma 1 and xn sigma n, so this is equal to this times this en, because this part is equal to 1, so multiplying by this doesn't change anything. So this is same as the previous expression of this. Okay, now we swap the rows of these appropriately to have this order. X sigma 1, x n sigma n. So now we swap these rows to have E sigma 1 and E sigma 2, E sigma 3, E sigma n. Okay, so since we uh, changed the order of these rows, then we must change the sign of this. But that sign is the same as this sign. So now we can get rid of this sign symbol from this summation. So that is kind of absorbed into the determinant here. Okay. Now recall the previous argument of 3 by 3 matrix. This this one, this expression is the same the as the determinant of x. So to be more precise, this is something like this: x11 e1 plus x12 e2 and x1n en. Oh, sorry, x1n. So first row x21 e1 x22 e2 x2n en and so on. xnn en, right? So actually by expanding using the multilinearity of determinant, you can show that this is equal to this. But this is actually equal to the determinant of x itself. Okay? So if we go back to here, then we just we have shown that this part is equal to the determinant of x. However, this part is equal to the determinant of y. So after all, the determinant of x and x times y is equal to the product of a determinant of x and determinant of y. So after all, determinant of xy is equal to determinant of x times determinant of y. So that is the proof. Well, I understand that this proof is quite abstract because we don't deal with any concrete numbers, and we deal with general n, general dimensions. So it's until you get used to it, it's very hard to grasp the idea. So I suggest you try this proof by limiting yourself to 3 by 3 matrices. So in this case, you can even 2 by 2 matrices is fine. So just consider, for example, 2 by 2 matrices like x11, x12, x21, x22, and also y11, y12, y21, y22, and try to calculate the product and then calculate the determinant. Then compare the determinant with the product of the determinants of this and this to see if this really holds and how this all these arguments apply to these specific cases of 2 dimensions or 3 dimensions. Now let's return to the definition of the determinant again. So the determinant of A was defined to be this summation. So we pick any row of the matrix, let's say the ith row. Then that is -1 to the power of I plus j, and aij, and this smaller matrix aij. Okay, so this I could be anywhere from 1 to up to n. And we still get the same result. Even if I is 1 or 2 or 3 or whatever, we always get the same number as the determinant. Or we could even choose any column rather than any row. So instead of choosing a row, we can choose a column. Let's say the jth column. Then we have this definition. Apparently, it's the same one, except for this summation. Instead of summing over j, we sum over I. So sum over each column, each row, by fixing a sum, fixing one j. Okay, we still get the same result. Therefore, it is easy to so once you understand this, it is easy to see that the determinant of A is the same as the determinant of A transpose. Next, we introduce a new notion of adjugate of a matrix. So here's a definition. Adjugate. Okay, let's say A is a matrix, a square matrix, n by n. Then we define its adjugate. So written A star, and we define this each element of this adjugate matrix as this. That is negative 1 to the power of I plus j, and this smaller matrix AJI. So instead of AIJ, we use AJI. So these indices are swapped. Okay, as usual, this AJI means from matrix A, we remove the jth row and the ith column. Then the remaining part comprises this matrix AJI. Okay. Now, using this, we prove the following theorem. Here's a theorem, and A is a matrix, square matrix, and A star is A's adjugate. Then we have the following. So A times A star is equal to A star times A, which is equal to determinant of A times identity matrix. And second, A has a right inverse. If and only if its determinant is non-zero. Okay, and three, if A has a right inverse, then A also has a left inverse. And these inverses are unique. Okay, remember, A's right inverse means some matrix B such that if you multiply A by B from the right, it becomes the identity matrix. So this B is the right inverse. And the left inverse is, let's say C is the left inverse here, then CA should be equal to the identity matrix. And we are saying if there is a right inverse, then A has a left inverse, and they are actually the same thing and unique. Okay, now let's prove this theorem. First, part 1. proof 1. And let's say Zij is this matrix product, A times A star, where A star is A's adjugate. Then each element of this matrix Z is given as this. Zij is equal to this summation Aik Akj star. Okay, and by the definition of adjugate, we have this A star Akj star is negative 1 to the power of k plus j, and this matrix jk. Remember, these indices are swapped. Okay, now if I is equal to j, then this summation is this. If then zi is equal to, so I is equal to j, so just replace j with I. Okay, so a I k negative 1 k plus I and a I k. Okay, but this is the definition of the determinant of A, right? So this is the determinant of A. Okay, so that's fine. And if I is not equal to j, then this is a determinant of some matrix which is not exactly A. Okay, but what is that matrix? So if you consider, so AJK is something like this. If you have A, you remove the jth row and the kth column. Okay, kth column. So you remove this, and the remaining part is this AJK, right? The remaining part is AJK. But the original matrix here was A, but if you replace this jth row with AIK, okay, so here we replace with AI. So AI1, AI2, and so on. So this row is filled with AIKs, okay? Then this whole expression is the determinant of this matrix, okay? We don't care about the elements of the kth column. It can be anything, as long as the jth row of this matrix is the same as the ith row of the original matrix A. Okay, but this I is not equal to j, so the ith row of this matrix also has the same elements, AI. So that means this matrix has two rows that are identical. So that means the determinant of this matrix is equal to 0 because it contains the same row twice. So if that's the case, then Zij is equal to 0, right? So that means the resulting matrix Zij is equal to determinant of A times Kronecker's delta ij. So that means the diagonal elements are determinant of A and off diagonal elements are 0. So that means Z is equal to determinant of A times identity matrix. So that's the proof of part 1. Wait a minute. We also need to prove this one. A star times A is equal to this. But the proof is very similar, so I will just skip it. Okay, next part 2. So suppose a right inverse exists. So there exists X square matrix such that AX is equal to the identity matrix. Okay. Then taking the determinant of both hands, we have AX determinant is equal to the determinant of I, which is 1. But as we have seen, the determinant of a product of matrices is the product of determinants of matrices, right? So this is equal to A determinant times X determinant. Okay, so therefore, the determinant of A is not 0 because this product is equal to 1. So it cannot be 0. Okay. Then, and so that proves the only if part. Then suppose determinant of A is not equal to 0. Determinant of A is not equal to 0. Then from part 1, from part 1, 1 over A determinant times A star adjugate is a right inverse, right? Because A times this matrix is A star, which is determinant of A times identity matrix, but the determinant cancels, so we get the identity matrix. So this is indeed a right inverse. So that proves part 2. And part 3, actually this proof also provides the proof for part of part 3. So part 3, first let's prove the uniqueness of a right inverse. Okay, so if we have two right inverses, okay, and also a y equal to identity. Okay, then if we multiply both sides by this 1 over A determinant and times A star. So in this case, let's see, AX equal to A star identity, but this part becomes identity matrix as we have seen before. Actually it's swapped, but we still have the same result from part 1. So after all, we have, and same for this one, so we have X equal to Y equal to 1 over this A determinant A star. So the right inverse is unique. That is this. And we can prove the same thing for the left inverse. And the left inverse is also equal to this. So if the right inverse exists, that is this. And the left inverse is also this. So that proves part 3. Now, since the right inverse is unique and the left inverse is unique and they are both equal to each other, so the inverse of A matrix A is denoted by this, A inverse. So this is both right and left inverse. Finally, we prove a little theorem involving the inverse of a product of matrices. So let's say A and B are matrices that are invertible, that have inverses, and then the inverse of A times B is equal to B inverse times A inverse. Okay? And of course, if these don't exist, we cannot calculate, we cannot get the inverse of AB. Proving this is easy. So just multiply AB with this. So B inverse A inverse. Okay? Because matrix multiplication is associative, so we can get rid of the parentheses. B inverse A inverse. So this is identity. So we have identity and A inverse, but multiplying by identity doesn't change anything. So that is this, and that is identity. So therefore, the inverse of AB is B inverse times A inverse. And you can prove the same thing for the left inverse. That is, if you multiply from the left, you can show that this is equal to the identity matrix. Okay, that's all for this lecture.